Hi, I'm Ben-Yaakov. In this presentation, I'm going to try to demystify the question of gain bandwidth product of a current feedback amplifier. Let me start off with the very general block diagram of a feedback amplifier, being a voltage feedback amplifier or current feedback amplifier. As was shown in previous electronic bits, the general block diagram includes a parameter G, which is a transfer function between the input to the summing point at the input. It can be shown very easily, and I'll go over it quickly, that we can divide the operational range of the amplifier into two frequency areas in which either beta A or the loop gain is larger than 1 or the loop gain is smaller than 1. For the case that the loop gain is larger than 1, then of course the 1 in this equation can be neglected. A open loop is divided out and we end up with G over beta, which is this expression here. We have to add the sign of the amplifier just to retain the polarity, being an inverting or non-inverting amplifier. However, when beta A is smaller than 1, then of course it can be crossed out and we end up with G over A open loop, which is shown here. So in order to get the response of an amplifier, and let's have a look at a voltage feedback amplifier first, we start off with 1 over beta. This crossover is in fact the point that beta A open loop is equal to 1. And for a different 1 over beta, a different closed loop, we have a different line. And the crossover point for each case is different. And this is why you get, this is being a minus 20 dB per decade line, and you end up with the fact that when you multiply the closed loop in the first case times the bandwidth in the first case, or the closed loop in the second case times the bandwidth of the second case, you end up with pretty much a constant number. So in this case, either you get a large bandwidth with a small gain, or if you need a higher gain, then proportionally you lose the bandwidth. Now what happens with a current feedback amplifier? Again, we can use exactly the same block diagram as shown before. If you are unfamiliar with the block diagram, please go back to previous electronic bits and it's explained there. Now in this case, G is the transfer function between the input and the summing point, and in this case it will be between the input voltage and the current flowing here in this resistor. So G in this case will be equal to 1 over R1 in parallel to R2, and this is as we look here. Of course in this case V out is assumed to be 0, plus in fact RA. Now what is beta? Beta is the current that we'll get from the output back into the input terminals, and assuming that RE is small, which is normally the case, it turns out that beta is approximately 1 over R1. So in this case, G over beta will give us, of course, the gain when beta A is larger than 1. And the question is, what can we do in order to change the bandwidth? Now, as I've shown before, the bandwidth of an amplifier is determined by the point at which beta A is equal to 1. The loop gain is equal to 1. Because in the area below this, the gain is G over beta. This is the gain. The area above it, the gain is G times A open loop, as we've seen before. So this is the crossover frequency, and this is the end of the bandwidth. Now, in the case of the current feedback amplifier, we have a very interesting situation. 1 over beta is determined by R1. Now, G in this case is approximately 1 over R1 in parallel to R2, which is R1 plus R2 divided by R1 times R2. Now, as we remember, the gain in this region is G over beta, and lo and behold, when we divide G by beta, or multiply it by 1 over beta, we get that G over beta is equal to R1 plus R2 over R2, and this is exactly what we would expect from a non-inverting amplifier. So what's the difference here between this case and the case of the voltage feedback amplifier? Well, the difference is that we have an extra degree of freedom. We can choose R1 independent of R2. You can choose it to be any value. If you choose it a higher value or a lower value, we have a different crossover, and then we'll have a different bandwidth. Now, once we decide on the bandwidth, we can go back, look at the gain that we want, G over beta, and select R2 to give us the gain. So we have an extra degree of freedom that we determine independently the bandwidth by R1, and then we can set the gain by selecting R2. This is entirely different from the case of the voltage feedback amplifier, in which case both G and beta are interdependent, and you cannot decide or select them apart. Now, the reason for this ability to change G and beta independently relies on the fact that G is buffered here by an amplifier, and this amplifier actually adds gain to G, and this gain, this is the gain of G, can be actually trimmed to any desired value. So there is a mechanism that allows us to independently change G to be independent of beta, which makes this possible. By this I mean getting a bandwidth which is independent of the closed loop response. Thank you very much for your attention.